So let's keep going here. We're going to do a little bit more nomenclature review, a few more challenging problems than what we introduced last time, kind of some special case scenarios involving stereochemistry, as well as branched alkyl groups. Okay, there are a few questions on your homework that has you practicing nomenclature of these branched alkyl groups, and they're kind of a pain in the butt, so we're going to go through that. Okay. One more thing here. Let's say that you come across a problem and it's got this branched alkyl group and you completely forget how you're supposed to name these things. Where should you look? The textbook. Awesome. Let's remember, we have a textbook for this course. It's provided for you free on Canvas, right? Under that course introduction module, there's a PDF that you can download of that full textbook. Okay, so don't forget that. That is a very good resource to use, especially with regard to reviewing this first semester material. For these branched alkyl groups, that would have been covered in sections 3.3 to 3.4 here. All right, so let's just take an example molecule. So if we're going to name this molecule, we're going to do the same thing that we always do. We're going to start by finding our parent chain. My longest continuous set of carbons are these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons here. That's my parent chain. What prefix do we use for 10 carbons? Dec. So this would be a decane here. That's my parent chain. But now when I move on to step 2 and I do my substituents, now I have this branched alkyl group here. I have to account for all of these carbons here, right? All 4 of these carbons, but they're not in a straight chain. This is not just a regular old butyl group. Okay, this is now a branched alkyl group. And we have 2 ways of dealing with these branched alkyl groups. The first is they have common names associated with them. These are names that are widely in circulation, but they're not technically the IUPAC name, all right? People would know what you were talking about if you used it, but it's not technically the systematic name, okay? The common name for this particular one, this would be an isobutyl group. These isos are always these branched alkyl groups that have a fork at the very end. By that I mean it splits at the very end. Okay? And importantly, and this is a very tricky thing about these common names here, the prefix that was used, but, corresponds to the total number of carbons that you see in that branched alkyl group, right? Not the longest continuous chain, but the total number of carbons. So there's 4 carbons in that branched alkyl group. That's why we use that but prefix. So again, total number of carbons. So the common name for this molecule here uses the common name for that branched alkyl group. All right, so my common name, I still got to indicate the position of that isobutyl group, 1, 2, 3, 4, 5. So 5 isobutyl decane. So common names are all well and good, but we don't have a common name for literally everything that you could possibly think of, okay? So instead, we also have an IUPAC name. To be clear, do we all know what I mean by IUPAC? IUPAC is the international organization that set the rules for nomenclature. So all these rules that we're following were set by an organization. And basically, historically, what happened is organic chemists were just cowboy chemistrying it up, calling their thing whatever they wanted, and we didn't call it the same thing in our lab as this guy over here in France called it in his lab. So everybody got together and was like, hold on, we need a way to do this, right? We need a common name or a common way to systematically name our organic molecules. So that's what we call the IUPAC. Okay? And for the IUPAC naming scheme, we play a very similar game to what we play when we do our parent chain and our substituents. We're going to now look at this branched alkyl group here. And within that branched alkyl group, we're going to find our longest continuous set of carbons. Okay? So now we need the sort of parent of the substituent here. So that would be this 1, 2, 3 carbon chain here. All right, that's my longest set of carbons, continuous carbons within that branched alkyl group. All right. The only thing that's sort of different from what we've been doing process-wise before, we also got to then name this substituent off of our substituent. Okay, this is a methyl. The only thing that's different here is when we number this parent of our substituent here, you always number from the parent chain of the molecule. So this is carbon 1. You don't number both directions and choose one. The carbon that's bound to your true parent chain is carbon 1. All right, so my IUPAC name for this here, for this branched alkyl group, would be 2-methyl. But then it's not propane because it's not the parent chain, it's 2-methyl propyl. You just keep that YL. And then importantly, if I'm going to now assemble and give you the IUPAC name of that compound, it's located at carbon 5 of my parent chain. Okay, so then in order to avoid confusion here, we're going to, really it's not my rule, the rule is that you put that branched alkyl group, that whole thing in parentheses. So it's 5-2-methyl propyl in parentheses, decane. All right, and just note that you run this all together here. There's no space or dash between our parentheses and our parent chain. So then in the assignment, just be careful because it will specifically ask you for either the common name, where you need to use the common name of that branched alkyl group, or the IUPAC name, where you need to use this systematic naming scheme. Okay? Cool, so branched alkyl groups. Another sort of complication of nomenclature that I can throw at you is what's called stereochemistry. And this kind of rears its ugly head in a few different ways, okay? One thing that I just want to say off the bat is you dealt with chirality the first semester. That's the RS stereochemistry. Great, wonderful. We're going to go ahead and just leave chirality in the first semester of the course. It turns out that that concept is really important for the reactions that you study in the first semester, and it's just really not that important for the subset of reactions that we study this semester. Okay? So your RS designation, we're not going to worry about here. Okay, well, again, we'll keep that in the first semester. So then what types of stereochemistry do we really need to worry about? So for cyclic alkanes, they can have what's called cis or trans stereochemistry. So let's take a classic cyclic alkane, our cyclohexane. Okay. If it has methyl groups on there, remember each one of these carbons has two other bonds that aren't explicitly drawn. All right. You discussed a lot about cyclohexanes, conformations, that chair conformation business last semester. We're not going to get into all that. The bottom line is it has two bonds. One of these bonds can be pointed up, and one of these bonds can be pointed down. All right, and we represent those differently. For a bond that's pointed out of the page, sorry, this thing's wigging out. All right, for a bond that's pointed out of the page, we use these wedges. Again, this means it's pointing out of the page, i.e. it's pointed up at me, pointed out at you guys. And then we can also use these dashed bonds. These are pointing into the page. So one's pointing out at you, the other's pointing away from you, pointing into the board here. All right, if these two bonds are pointed in opposite directions, that would be the trans stereochemistry. If they were both pointed in the same direction, either they were both wedges or they were both dashes, either one would be considered the cis stereochemistry. Right, so both of these are cyclohexanes. Both of them have two methyl groups on there, spaced just one carbon apart, right? But they are distinct molecules. They will have distinct boiling points. They will have distinct reactivity, all that sort of jazz. Now, they're very close to one another. Don't get me wrong. The boiling points are going to be very similar, but they're not identical. They are, strictly speaking, distinct molecules. If we're going to name this compound here, then, we have to include that stereochemical designation because we have to uniquely point to one of these two, all right? So if I'm naming it without my stereochemistry, they would both be 1,2-dimethyl cyclohexane. All right, and that's true for both of these, which is again why we have to include that stereochemical designation. We put that out front, so this would be trans 1,2-dimethyl cyclohexane, and the other one would be cis 1,2-dimethyl cyclohexane. Okay. All right, the other stereochemistry is going to pertain to alkenes. Okay, and some alkenes you can actually use the cis-trans designation for as well, but there are some that you can't. And so there's a more universal system that we built, which we call our EZ stereochemistry. All right, so let's take a look at two alkenes here. before we worry about stereochemistry, everybody just take a second and name that first alkene for me. Okay, my longest continuous set of carbons are these 5 right here. Remember, when I number my parent chain here, I'm going to give that double bond priority. So the only thing I'm going to pay attention to is making sure that double bond has the lowest possible number. All right, and I have this methyl substituent here on carbon 3. So this would be 3-methyl 2-pentene. Okay, and I want you to take a second and convince yourself that if we named this other molecule here, we would get the exact same name, 3-methyl 2-pentene. Okay? Now, not only do these molecules look different, they're drawn differently. Importantly, this easy stereochemistry arises from the fact that unlike single bonds, double bonds cannot rotate. So these groups are locked in these positions about this double bond here. All right, so these are 2 distinct molecules, and so we have to name them with their proper stereochemistry, just like we did our cis-trans structures. All right, but again, we're going to do so using this EZ nomenclature here. So how do we assign E or Z? What we're going to do is we're going to chop this molecule at that double bond. I'm going to say hiya, down the middle, boom. Okay? And what we're going to do is we're going to look on either side and we're going to assign the 2 groups high or low priority. Okay? So we're going to look left. Assign high and low priority. And what is this priority based on? Atomic number. Oops. Cool, so what do I mean by that? Again, I'm going to chop it at this double bond, and I'm going to look on the left-hand side of this bond, and I'm going to assign these 2 groups high and low priority. Okay? I see this methyl group written here, but I said there are 2 groups. What is the other thing bound to this carbon on this side? My implied hydrogen, right? My carbon needs those, however many, 4 bonds. So I have to fill in with my mind's eye this hydrogen here. Okay? So we're going to compare these 2 atoms that are bound to this carbon on the left-hand side. I have a carbon over here because it's a methyl group, and then I have a hydrogen that's implied up here. Which one's going to be my low priority group? Which one has the lower atomic number? Hydrogen. Hydrogen's always your low priority group. All right, so this is my low priority group. The carbon is my high priority group. And now I'm going to jump to the other side of my double bond, and I'm going to play the exact same game. So now instead of looking on the left, we're going to look on the right, and we're just going to assign high and low priority. So if I have this in this particular molecule, I'm going to be comparing this carbon with this carbon, right? Well, all of a sudden I have a tie. Both of those are carbon atoms. Neither one's got a higher or lower atomic number. So how do I break this tie? Okay. To break a tie, we're going to list all the other atoms that are bound. Okay, so what do I mean by that? We said that this was a carbon here. Let's look at this top one, this methyl group. Well, what are the other 3 bonds on that carbon atom? Hydrogen. So what we're going to do is we're going to make a list here. This carbon is bound to 1, 2, 3 hydrogens. We're going to look at our other carbon atom. What is that bound to? It's bound to 2 hydrogens, but then what's the third bond? That other carbon. So my list here is carbon, hydrogen, hydrogen. And we can see that in my list here, I have an atom with a higher atomic number, making this my high priority group. So the ethyl group's high priority, and the methyl group is low priority here. Okay, so then to assign our E and Z stereochemistry, if our high priority groups are on the same side of that double bond, that is the Z stereochemistry. If it's on the opposite side, that's the E stereochemistry. So looking here, which one would this one be? The E or the Z stereochemistry for this molecule? I got my high priority group pointed on the same side as my other high priority group. So this is the Z stereochemistry. All right, we build that into our name by putting it in parentheses out front. Okay. What's also acceptable, and what you have to do if there are multiple double bonds, is to indicate the position as well. So 2Z, 3-methyl, 2-pentene. Either one of these are acceptable. All right, so it's the Z stereochemistry if it's on the same side. It's the E stereochemistry if it's on the opposite side. Sometimes if you just have the stupidest little phrase, it'll help you stick in your mind and remember. So for this, we remember that the Z stereochemistry is when those 2 high priority groups are on Z, same side of the molecule. On the same side. But if they're on Z, same side, it's a Z stereoisomer. All right, and I'm going to leave it to you to convince yourself that our other stereoisomer here is our E stereoisomer. Cool. All right, so now we're going to switch gears a little bit and we're going to start talking about some experimental techniques. All right, first thing we need, both of which that we're going to discuss are types of spectroscopy. So let's just talk about what the heck spectroscopy is. Okay, so spectroscopy is, there are several different forms of spectroscopy, but they all have the same basic setup. All right, what we're going to be doing is we're going to be using photons and their interactions with atoms. to take certain measurements. And depending on what photon we use, we're measuring different things here. Okay? So they have all the same basic setup. You have some source of photon, right? To be clear, by photon, I mean electromagnetic radiation. So the lights coming down at us right now are an example of photons. So you can have a light bulb as your photon source. That's what that's supposed to be. I'm not an artist. All right, that's a light bulb here. Okay? What you do is you have your photon source, and it's going to send in a bunch of different photons. So these are photons of different wavelength / frequency. Okay, you send those photons through your sample. So here I have a sample container. And what happens is some of those photons get absorbed and others just pass right through. They don't interact with your sample at all. And then you just measure what comes out the other side using a detector. All right, there are several different types of detectors that you can use. They're sort of just fancy little photon counters. Okay, so this is the same setup for all different types of spectroscopy. You're sending in photons, you're seeing what comes out the other side. Some get absorbed, some don't. They just pass right through. That's what we're measuring for our spectroscopy experiments. Okay, so first of all, this whole thing of spectroscopy takes advantage of the fact that photons interact with the particles that we're made of. The protons, the neutrons, and the electrons. That in and of itself is already pretty cool. The universe is filled with tons of particles that we don't really talk about because they don't interact with us at all. There are muons and neutrinos passing through you right now, and you have no freaking clue because they don't interact with the protons, neutrons, and electrons that we're made of. Okay? Photons do. And so basically this whole scheme of spectroscopy is us chemists taking advantage of those interactions to take certain measurements. All right? So your type of spectroscopy is going to depend on the type of photon that you use. By that I mean where on this electromagnetism spectrum you are here. Photons can have a very wide range of frequencies or wavelengths, right? Frequency and wavelength are inversely proportional. You can have really small wavelength photons like X-rays, or you can have very large wavelength photons like radio waves. And we're talking about orders of magnitude difference here in terms of these photons, right? So the different photons, where on this spectrum you choose, will give you different information. The one that you've covered already would be UV-Vis spectroscopy. This uses light from the UV invisible region. Okay, so the light that we can actually detect with our fancy detectors we got built into our bodies, our eyeballs, is really just a small sliver of this electromagnetic spectrum. We can only perceive wavelengths from 400 nanometers to 700 nanometers. There are smaller photons, we don't see those. There are larger photons, we don't see those, right? In this region here, that's what we call the visible region, and just outside of it is what's called the UV region. That's what's giving you your sunburns. You can't see those UV rays, but they're still interacting with your cells and doing some damage. So UV-Vis region, within this region are photons interact with the electrons in a molecule. Okay? So it turns out that why stuff has color associated with it is because within that region, within that visible region, those photons are interacting with the electrons in atoms, right? So the reason that this appears purple is because the light coming down is hitting those dye molecules in there, it's exciting those electrons and then bouncing back to you, all right? And that's why it's sort of appearing purple, is because it's interacting with those electrons, okay? So in this UV region, very cool, we can sort of understand how color works. That's obviously a big thing. The other thing that you use it for, like 99.9% of the time, is that your signal that you get at the end is directly proportional to concentration. So you can sort of qualitatively use it to get an understanding of where a certain dye molecule, for example, absorbs in that region. But practically speaking, 99.9% of the time when you use this technique in the lab, it's because you want to know what the concentration of something is, right? It's a very convenient way for measuring concentration. Okay, so the one that we're going to introduce now is what's called IR spectroscopy. This uses photons in the infrared region. All right, if we look at our electromagnetic spectrum here, these are now photons that are longer than what we can perceive with our eyeballs. Okay. Fun fact, I first learned about this by reading it in a book, and I said this infrared spectroscopy in my head for about 2 years before I realized that that was the wrong way to say it, and I still mess that up on the reg, all right? So if I say infrared, I really mean infrared. It is just seared into my brain in the incorrect way here. Okay? So in this region, photons interact with covalent bonds. So perfect for organic chemistry where we're specifically focused on covalent compounds. This is a type of spectroscopy that, depending on where in the region you absorb, different covalent bonds will absorb different wavelengths, right? So we can see certain bonds using this type of spectroscopy. So in terms of what information do we get, that's what information we get, what bonds are present. And specifically, right, we call those our functional groups. So for example, an alcohol will give us a very different signal than will a carboxyl group, et cetera, et cetera. So we can see certain functional groups in this IR spectrum. That's what we use it for. All right? So importantly, our cons. What does IR not tell us? Well, it tells us no information about the size or shape of our molecule. So all alcohols will give us pretty much the same signal. If you have 4 carbons versus 10 carbons, you really don't see that in an IR spectrum. Okay? So the pros, though, is that A, we can see our functional groups. Cool, that in and of itself is a good bit of information. The other reason that you use it just so frequently is because it is so easy to use. You literally just go put some sample on a thing and press go, right? No brainer. There's no amount of training you need for an IR. The instrument itself is, in the grand scheme of things, relatively cheap. You can get a good IR for $15,000, which, I mean, you're not going to go get one for your bedroom. But in the scheme of lab equipment, that is on the lower end of cost here. All right, so very affordable, very easy to use. All right, those are sort of your pros. So we got easy to use and affordable. We're going to discuss another type of spectroscopy called NMR, which is kind of the exact opposite. It gives you so much information about your molecule. You can figure out the exact size and shape of your molecule from NMR, but it is the exact opposite. Those instruments are millions of dollars. They take a lot of training to use correctly. You got to build a special room for them because it has this giant magnet in it, right? So you got kind of our two extremes of spectroscopy. One of them is going to be super easy to use, doesn't give you all that much information. The other one we're going to discuss is the opposite. You get so much information, but it's a pain in the butt and kind of limited in your use for it. Okay? Again, we're going to focus on IR here to start out with. Okay? We said that it interacts with our covalent bonds. So when we think about covalent bonds, we have these two atoms bound to one another through that covalent bond. We oftentimes think of that covalent bond as kind of like a spring, right? Because molecules are never sitting still. They're always kind of moving around and vibrating. So within that bond, those two atoms are vibrating back and forth, okay? So when an atom absorbs a photon in the IR region, in the infrared region, what it's doing is you're exciting its vibrational state. So at first it's just vibrating slowly, it absorbs that photon, and all of a sudden it starts vibrating much more rapidly, right? So we excite these bonds in terms of what's called their vibrational states. There's also some more complicated stuff about, like, you can also excite them rocking. The bottom line is you're getting those bonds moving again, okay? They're sort of moving, and that's why they're absorbing those photons. Okay, so our goal for IR spectroscopy is to learn patterns that correspond to certain functional groups, so that when we see, for example, the IR of an alcohol, we're like, yep, that's an alcohol because I see that alcohol peak in there. All right? So the first thing that we do when we do our analysis of an IR spectrum is we cut it up into these different regions. All right? So first of all, in UV Vis, you use your x-axis is wavelength is typically the default. For IR, the x-axis is frequency, what they call wave number. Okay, so this is the frequency of photon that you're sending in, and then you're going to measure what's called the percent transmittance. Again, this is just a measure of how much comes out. Okay? So different bonds absorb in different regions here. Our single bonds absorb at the lower end of our spectrum. Double bonds in this intermediate end of our spectrum. Triple bonds in this region, and then finally anything that's bound to hydrogen up at the top end of our spectrum. Okay? So the first thing that we do when we do our IR is we cut up our spectrum into these different regions. And here they use these exact values. I like to use just nice round numbers here. All right, so let's do an example. Here's an IR spectrum. On the bottom is the wavelength of the photon that I've sent in, and on the top is my transmittance, or rather on my y-axis is the transmittance. So these peaks right here, these downward facing peaks, are showing me photons that are being absorbed. Okay, so the first thing what we do is we're going to cut it up at 1500. Everything below 1500 is what we call the fingerprint region. From 1500 to 2000, that's our double bond region. From 2000 to 2500, that's our triple bond region. All right, and then anything greater than that is the something bound to hydrogen region. All right, so that previous slide gave you sort of more exact numbers. I think 1600 is technically where you can start, whatever. We use nice round numbers, way easier, right? You put in these cut marks at 15, 2000, and 2500, and that divides up your spectrum, the important regions of your spectrum. Okay? So the fingerprint region. Your lab instructor might tell you sort of specific things to look for here. Generally speaking, we take that fingerprint region and we straight up ignore it. Okay? Much like a fingerprint, it is very useful for something like a database that can scan a bunch of known compounds and see if they overlap, they match that fingerprint region. For us, it's just too freaking busy, right? There's too much going on in the fingerprint region to really make sense of it. There are certain things that you can look for in that region. Again, I'll leave it to your lab instructor to sort of point those out when you get to it. All right? Generally speaking, we ignore. Okay? So what can I say about this compound? Does it have any double bonds? Yes, I have that giant peak in the double bond region. Does it have any triple bonds? No, we got nothing in that region. Does it have anything bound to hydrogen? Yes, I got this sort of cluster right here in my something bound to hydrogen region. Okay? So again, first thing we do is we cut it up into these regions here. Depending on where our peaks are, that tells us about our, the types of bonds we have in our structures. Okay? Okay, so first types of bonds that we can spot. Obviously going to be very important because all of our organic compounds contain carbons and hydrogens. So what do these bonds look like in our IR spectrum? First of all, which region are they going to absorb in? Carbon-hydrogen bonds. Where would that be in this whole thing? Are those going to be in the double bond region? Are those going to be in the triple bond region? No, they're going to be in the something bound to hydrogen region. All right? So where they are in this region, though, is going to tell us about the type of carbon. So in particular, the hybridization of a carbon is going to influence where it absorbs in this region. Okay? The lower end is this 2900 thing here. All right? And let me just point out, because this is a great example, this right here is my carbon hydrogen, my sp3 hybridized carbon hydrogen peaks. Every organic, not every, but just about every organic molecule you study is going to have some sp3 hybridized carbons and hydrogens. So you will see this cluster of peaks in every single IR spectrum that you look at, right? Because all organic molecules have those carbons and hydrogens. Which goes to say, like, that particular peak doesn't tell you too much other than, yeah, correct, we have an organic molecule, right? Because again, you'll see it over and over again. All right, what we'll notice is that if we look at our other ones, they absorb higher than that. Right? And in fact, they all absorb higher than 3000. So the other thing that I like to do when I cut up my IR spectrum is I'll lay down one more line at 3000 to help separate my sp3 hybridized carbons from any other that might appear. Okay? So let me just show you an example of a compound that does have an sp2 hybridized carbon hydrogen. These are two overlaid on one another. So one of them is octene in blue. The other one is just octane, right? And so what we can see is these spectra, they match pretty closely, except now I have in my double bond region, I'm going to lay down my cut marks here. Now I have a carbon-carbon double bond peak, right, for my octene, because that's an alkene. And the other thing that I see that jumps out is when I lay down that 3000 mark, now I have this little peak over here. And again, this little one is going to correspond to the sp2 hybridized carbons and hydrogens, carbon-hydrogen bonds. All right, so this little mark at 3000 here will distinguish the cluster of peaks that we always see, our sp3 hybridized carbons and hydrogens, from any special ones that we might have. If it was a triple bond, you would just expect it to see shifted even more, right? Around the 3300 region. So here is just sort of those examples stacked next to each other with that line at the 3000, the 3000 mark sort of laid in. Again, an alkane won't have anything over here. An alkene, you'll have a peak just to the left, and an alkyne will be even further to the left around that 3300. Okay. I honestly am not exactly sure what resources you use in your lab. I assume you have like a lab manual or a lab textbook. Do you have a manual or a textbook? It's a textbook, cool. Somewhere in there is going to be an appendix that has a list much like this of these sort of regions where you typically see these absorptions happen. Cool. So the last one that we'll cover here today, just to get it out of the way here, are alcohols. Alcohols are the easiest functional group to spot in an IR spectrum. Okay. First of all, that alcohol group is OH. So where would we expect this to absorb? All the way on the left-hand side in the something in H region. Okay. An alcohol peak is always this very distinct, very broad peak here, okay? So an alcohol, that OH group in particular, will absorb in this 3200 to 3600 region. Notice that it's above that 3000 mark, that sp3 hybridized carbon and hydrogen. And what really is going to jump out at you is just how strong and how broad that peak is. Most of our peaks are nice and sharp little peaks, okay, like what we've seen up until this point. An alcohol's distinguishing factor is this broad peak in this region. Again, lying just to the left of our sp3 carbons and hydrogens peak, right? That's what this is here. So our OH group is, again, this big, broad peak that we see here. Okay, so again, we're going to be learning patterns that are going to correspond to functional groups such that if we put our sample on and we press go and we get a spectrum like this, we say, ah yes, there is an alcohol in that molecule. Okay, cool. We got a few more patterns that we're going to learn here, and then we'll move on from IR. Awesome.